So thanks a lot, everyone, for joining us today. Today we have with us Michal Stechly, who is a quantum software engineer at PsiQuantum. He is the lead of developing Bartik, which is a tool for performing symbolic quantum resource estimation. Previously, he was at Zapata, where he was leading the efforts of developing BenchQ, which is a resource estimation tool developed as part of the DARPA's quantum benchmarking program. His main interest lies in building better software tools for quantum computing, in particular, through designing better abstractions. Michal is also an active member for the community and has been involved in multiple initiatives from QAOSIP mentorship program, Unitary Fund, IEEE Quantum Week conferences, and now Womanium Quantum as well. He's also the author of an amazing blog called Musty Thoughts. Personal recommendation, if you haven't gone through his blog yet, I would really encourage the participants to go over there. Pretty complex concepts are also written down in a very easy to read format over there. Like, I really enjoyed going through that. So yeah, but coming back to today's lecture, today we have Michal talking about what to do with an algorithm if you can't run it. So a brief introduction on quantum resource estimations. Over to you, Michal.
Thank you very much for for having me here, and thank you very much for this kind introduction. Hello, everyone. I already got introduced, so there is really not much more to add on this. So today I will talk about, I divided my presentation in three main sections. So first is, what's the difference between NISQ and fault-tolerant quantum computing? Because my understanding is that most of the program so far was focused on more NISQ things, and I would like to tell you a little bit of like how it's different from the fault tolerance, which is what I'm mostly working on. Then what are some main challenges in the development of applications and algorithms for fault tolerant algorithms, and then role of quantum resource estimation in all this, an overview of like what are like some different QRE methods or like pieces of software that like people use. So, well, that was already said. So I work at PsiQuantum. I am a quantum software engineer at PsiQuantum, and our mission is to build the first useful fault-tolerant quantum computer. We are based in Palo Alto, California. The company has been founded in 2017. And the approach that we have for the hardware, which is, I would say, not particularly popular, is integrated photonics. We believe this is kind of better and more scalable way of doing quantum computing. However, it's very different from the other approaches that you might be more familiar with, like superconducting qubits or ion traps. So I won't be getting too much into the hardware, but it's pretty interesting, how it works. So if anyone is interested, feel free to reach out to me. I can provide some details. And we are exclusively, focused on error-corrected, fault-tolerant quantum computers, and scaling the computers from, to actually thousands of or millions of like logical qubits. And we are not really that interested in building like smaller prototype. So you'll see like how this is like somewhat different from probably some other approaches that you've seen so far. Okay, so with that brief intro, let me dive into it. So we can take a look at different quantum algorithms, quantum circuits, by looking on the space-time trade-off. So that's basically, time is operations. The more operations you need to execute, the more time it will take, right? If you have one gate in your circuit, it will take about 100 less time to execute than if you have like 100 gates in sequence. So operations is one thing, and the other thing is like how many physical qubits do you need to actually run the algorithm. In case of NISQ algorithms, those numbers are both pretty small. So, you need relatively small number of qubits and relatively small number of operations. However, what is specific for NISQ algorithms is that, for example, in VQE or QAOA, in order to get a single estimation of the energy, you need to repeat the same circuit many times to get good statistics on what the expectation value of the given operator actually is. And then the problem is that even further, when you try to run many, you need to obtain many values of those energies, because the algorithms are heuristic, and you need to optimize the parameters in your ansatz in order to actually get to the correct result. So even though initially it looks like, well, I only need, I don't know, like 100 physical qubits, and I only need to execute, a couple of hundred operations, once you start stacking this up, it actually takes much more time, even if it can be run on like smaller number of qubits. So this is very different from the fault-tolerant picture, where, well, we are talking about millions of physical qubits, and we are also talking about billions of logic of operations that you need to execute on this computer. So definitely there is, those two approaches require different mindsets, different methods, and I will be talking a little bit about it. But this picture here with the logarithmic scale shows kind of how different and like how actually far away those two realms can be. And to talk about an example of where why, for example, we at PsiQuantum think that NISQ is not like the most promising approach, and also to show you why in the topic of resource estimation, it's really hard to do resource estimation for the variational quantum algorithms, and it's much easier to do that for fault-tolerant algorithms. I will show you an example of a very simple application, which is calculating the ground state energy of water molecule, right? So this is a toy problem. There is no scientific or commercial interest in that, but it's a good example that can give you some idea of what are the differences, and why, even though with fault-tolerant algorithm we see really big numbers, they're not necessarily as scary as they look. So I would say there is a lot of this those slides are based on the paper by Jerome Gontier and others, by Zapata, published in 2022. It's really good paper. I have to say, like, I've been at Zapata when we were publishing it, and like it really produced a lot of excitement and discussions. But there is a lot of the assumptions that go into that. I don't want to, I don't even understand quantum chemistry well enough to explain properly what those assumptions actually are. But basically, whenever you have a problem, like quantum chemistry problem, and you need to run some algorithm, then there is a lot of the choices on the classical preprocessing that you need to make. So here is what some of those choices are. Then another thing is that there are some assumptions about the hardware here, and then for the kind of NISQ algorithm, what has been used is like VQE with some hardware efficient ansatz. And there are, if you read the paper, there is like some calculations about the constant factors needed to actually perform this calculation. So looking at like very similar picture, right? If we take a look at the NISQ circuit that we need to run, it requires for this water molecule around 80 physical qubits, and requires about 400 operations, which is roughly 40 microseconds, given the assumptions from before. But it turns out that if you want to estimate the energy of the like ground state energy of this molecule down to the accuracy that is actually required to beat the classical computers, you need to repeat this one circuit about 2 billion times. And this gives you about a day worth of nonstop calculations needed to obtain only one energy estimation. The trick is that with the variational algorithms, like one energy estimation is not enough to really solve the problem. You need to find what are the optimal parameters of the ansatz you have. So in this case, like VQE hardware efficient one, and no one really knows how many iterations that requires. But you can safely assume that it will require more than 100 iterations, which means that this whole algorithm would run for about 3 months. And this is like one of the issues that we've seen at Zapata at that time with the variational algorithms. And for me personally, these results were one of the things that prompted me to look more into the realm of fault tolerance. And it turns out that if you take some of these things into account, you will start digging into what fault-tolerant quantum computing actually is, what it requires. You will come up to a couple of conclusions. It turns out that for the applications, that for the fault-tolerant quantum computing, there are many things that are different, and like applications are different. It just like makes sense to look in different applications than it makes sense to look at the NISQ devices. I mean, there is some overlap, but definitely I would say there are like big differences between those two communities when it comes to like what problems we're trying to solve with quantum computer. The algorithms are totally different. Variational quantum algorithms is what most people try to run on the NISQ device, while this is something that would be pretty wasteful to trying to run on the fault-tolerant computers. Compilation is also different. So like how you take the algorithm from like high-level idea and actually translate it to executable like instructions. And then necessarily, because all those other things are different, you also need different types of software. So I will actually talk about mostly about the algorithms and compilation right now. And I would say that the software part kind of follows. So why am I saying that the algorithms are different? So I forgot to put a slide of how does the circuit for variational algorithm looks like, but I hope you've seen these quite a lot before. But you basically have this circuit, and the circuits basically, if you print it out, it can fit on a screen, sometimes maybe on a couple of screens. This is not the case with the default tolerant algorithms, right? They are much more much bigger, and I would argue much more complicated. So the most prototypical, I think, algorithm is, or one of the most prototypical is the algorithm of like phase estimation, and it roughly looks like this, right? There are like some qubits that we use for eigenphase and like eigenstate, And then we have a unitary matrix U, which gets into the circuit itself. Basically, the circuit is mostly consists of many repetitions of controlled version of this unitary. But then, what this unitary even is. Well, if we take an algorithm that we like, just like speaking of like we as like our team at PsiQuantum, it's there is an approach for encoding the matrix that we want into U called block encoding. And one of the block encodings for quantum chemistry problems is called double factorization. And again, like it's described in details in the paper here. But if you take a look at figure 16 in that paper, the circuit looks something like this. And well, the problem with this picture is that it actually, each of those like smaller subroutines is like pretty complicated itself. We can, divide the circuit into the parts like select, prepare, and reflect, right? So some of those parts are kind of repeated, maybe not verbatim, but those two prepare blocks are pretty similar. They only differ with this one control here, though the selects one are also related. But if we actually take a look at each of those blocks, we can see that we reuse some of them. And those blocks that we have as purple here, they are basically used to load classical data on a quantum computer. And this is a routine called QROM. And as you can see, we have like a bunch of those QROMs here. So let's take a look how such a QROM looks like. So if we take a look into the structure of QROM, we see that it can be decomposed into something like that, where the question marks here, they can be either like 0 and 1, so like either nothing or black dots, depending on what kind of classical data we are loading onto this. So you see that this actually doesn't look much like a lot of the circuits we use in variational algorithms. In variational algorithms, usually there are some, I would say like plenty of rotation gates, some CNOTs, etc. However, here we have a lot of multi-controlled gates. And also, as you can see here, there's like not necessarily that many of rotations. We try to avoid rotations in fault-tolerant algorithms because they are pretty costly, while they're not that costly for NISQI devices, right? So as you can see, what I'm trying to say here is that rather than having some circuit that is maybe not yet, rather than having some circuit that is relatively small, we actually go through those stages of those levels of hierarchy of different components that we need to implement to have a working circuit. And also they simply look very differently and behave very differently from what we have for BQAs. So if we look at a circuit, there's just like some random circuit that looks like that, and we look at it through a kind of NISQI metric, then basically some of the operations are cheap, and those 1 qubit operations are usually very cheap. Some other operations are expensive, right? So 2 qubit gates, CNOT swaps, whatever, they're more expensive. And cheap and expensive is somewhat relative term here. But what we mean by that in the NISQI realm is that some operations are cheap. So like the ones that are expensive usually either take more time or more importantly, introduce much more error into the system, right? Because the 2-qubit gates usually has much lower fidelity than 1-qubit gates, so we try to avoid them. So whenever we want to compile our program for a NISQ device, well, we try to avoid the red stuff, and we're pretty okay about the yellow stuff, right? And that's kind of what we're aiming at. However, if we look at the fault-tolerant circuits, the situation is very different, because everything that's green is so-called Clifford gates. So these are basically almost all, all kind of standard 1-qubit gates plus CNOTs. And these are basically CNOTs. And these are basically for free. There are like some, let's say, like accounting tricks that you can do so that you don't really need to worry about how many green gates you have. What's kind of relatively cheap is measurements, but there is some cost associated with measurements, so you also want to be a bit careful about it. But what's actually extremely expensive are those T gates and also rotation gates. So for certain reasons, implementing a T gate requires a lot of resources on a fault-tolerant computer. And basically, that's to the level where when we are estimating the cost of the algorithm, we sometimes just provide the cost in the number of T gates, because that's really the only metric that's relevant, because everything else is just very, very cheap compared to how much it takes to implement a T gate. So yeah, so this is this means that how we treat a circuit and how we optimize it to run on like NISQ or fault-tolerant device is just like very different. And further, I would argue that when you have you compile for NISQ hardware, you basically try to get rid of as much of the red as you can and try to get as much yellow as you can. And if you can transform your circuit in such a way, then you did a good job. However, for fault-tolerant devices, getting rid of the red stuff and introducing as much of green as possible, if you can, is only kind of one way to, like, one little step of the compilation. Because once you did this, you actually need to translate it to something that the hardware can understand. So, for example, if you follow the formalism that's explained very well in the Game of Surface Codes paper by Daniel Litinsky, you can translate a circuit like that to a collection of so-called PPMs and PPRs, right? So those are big Pauli product measurements, Pauli product rotations. I won't get too much into the detail, but basically the thing is that you can translate any circuit into a circuit that looks somewhat like this. And then, thanks to a technique in the error correction called surface codes, you can actually use those operations to translate them into something that is actually error corrected, right? So, for example, okay, I will very much like skim over this. Don't worry too much about what is specifically on the slide, but basically what we have in maybe this picture is that every single cell here corresponds to a logical qubit, right? So this is not a physical qubit that you have on the device yet. This is a logical qubit, and you can group some of those patches to create, you see those like kind of small patches here. And if you want to perform an operation that's described as this like Pauli product measurement, you just need to kind of connect appropriate patches in appropriate way. And there's, again, like, it's this really, really well explained in that paper. But what I want to show really is how this connects to the hardware later, because on some level, each of these patches here, each of these logical qubits can be seen as d squared, sorry, d squared physical qubits, right? So where d is the side of the square, right? So basically, in this case, in this picture, you have 25 physical qubits for each logical qubit, right? And then each of those operations that need to happen, they are happening, between basically all those physical qubits. So in order to perform like a relatively simple operation on the logical level, you need to perform pretty, complex operation on the physical level, because this operation will involve a couple of d squared of those qubits. And usually the d is not of the order of 5, it's more of the order of like 20 something. So we are talking about, hundreds and thousands of qubits, physical qubits, that you need to perform those operations. Which is, again, just to the point that when you're talking about fault-tolerant systems, the mindset is very different. And this is a trap that, a lot of the people kind of fall into, because, if you take a look at those two, Intel processors, and you think about something that's, older and not as good, you can think about a processor that looks like this. But then if you think about the more modern one, you think about this like, i7, for example. And this is sometimes how people look at the difference between NISQ and fault-tolerant, right? Okay, so I would just have this processor that works similarly to what I already have, but it's just better. But actually, at PsiQuantum, we think this is not the right way to look at it. We think that a much better comparison is to think about it as, Intel 8086 and a Frontier supercomputer, because the complexity to actually use this device is kind of so much difference, and you cannot use the same mental framework really to program, these two pieces of hardware, and you need very much like different infrastructure, different architecture, and different approach to design of software and applications around it. So, okay, that's kind of closes the part when I talk about what's the difference between NISQ and fault-tolerant algorithms. Algorithms approaches. Now I wanted to tell you a little bit about what I kind of work on a lot, which is what are the challenges in the development of algorithms and applications. And well, I think no one expressed it better than my friend Yuval, who had a talk a couple of years ago titled "Why Are Quantum Algorithms Papers so very much long?" And we internally call it, 100 pages paper problem. And yeah, that's it. Like, some of those papers are really just like that long. So if we take a look at the one about the double factorization that I was showing before, as you can take a look at that, and you see that this paper actually has like 75 pages, I believe, or 73, which is quite a bit. And it takes a lot of time to go through that paper, understand what's going on, understand how to actually implement this algorithm, how to implement the circuit. So it's definitely, it's definitely tricky. And, another thing is that often when we talk about the algorithms, you can see that, this algorithm provides a quadratic speedup or exponential speedup or some other speedup, right? And in order to do that, you need to be able to calculate the kind of analytical, like analyze the complexity of the algorithm and like calculate analytical expressions for the costs of implementing the particular algorithm. And actually, when we do that, we did that for like some projects in the past. And the problem is that doing this actually takes, again, like a lot of space and a lot of custom code that, well, you just need to implement in order to do this. And it really takes months to write such code in such a way that it's correct. At the same time, another thing that I feel some people are, or maybe let's put it this way, like we are very much aware of at PsiQuantum, and some other people have different kind of perception of that, is what are the timelines? And we think that really fault-tolerant systems are not that far away in future. And I understand the argument that like some people say that, similarly with, fusion, it's always 5 years away, and with quantum computing, it's similar. But actually, I believe it's, this time it's really not that far away. And you don't need to take kind of my word for this. IBM plans to have the first fault-tolerant quantum computer by 2029. IonQ also in some materials basically says that they want to have fault-tolerant system in like 2028. And we, in some of the recent press release, we said that we want to have operational quantum computer by end of 2027, which is really, just 3.5 years from now. So on one hand, it's very optimistic. It's like great that we might have, maybe some of those people will fail, maybe there will be delays. But again, it looks like end of decade is not out of the question. And what the problem we have with applications is that, if I could just like today conjure a fault-tolerant quantum computer using magic wand, time machine, whatever, the question is like how many practical problems I will be able to solve with what's available in the public domain, right? I mean, maybe someone has written down somewhere the algorithm and like all the software that has it, and they figured out all the applications, like thousands of applications, but no one knows about it, so it's hard to say. We're talking only about the public domain. So I'm curious what people think, what the number of that is, and like how many problems can we solve? I'm giving you like 15 seconds.
So waiting for the answers on the code. We have a few people typing in.
Okay, so what are the numbers?
Yeah, still receiving the answers. 10 to 30. Mohammad Reza from Iran mentions.
Okay.
5.
So, sorry?
Maria Dinsha from Romania mentions 5.
Okay. So up to my best knowledge, there's perhaps one practical problem we could solve if, a computer magically appeared. And this is a factoring problem. There has been some recent papers by, definitely by Daniel Litinsky, I think by Craig Gidney, but maybe someone else, I'm not sure, where they actually, figured out the compilation of those very complicated hierarchical circuit down to something that's actually, most likely runnable on a quantum computer. But for example, if you think about a lot of the I don't know, like materials quantum chemistry applications, it's not that obvious that you could just like compile those circuits today. For example, the one about double factorization that I showed you before, and just run it on a fault-tolerant quantum computer. A lot of the things, is not properly tested. A lot of the things is not really, I would say, like, I talked with like many people in different organizations working on those compilations projects and those applications, and they are very much not confident that the compilation that they have figured out actually gives correct result, right? And so one of the very interesting projects that I was part of was DARPA's quantum benchmarking program. And that was when I was at Zapata. And basically the goal of that problem was to find practical applications that if we could use quantum computer to solve them, that would be cost effective, and also provide some, resource estimates for, well, how big of a computer we actually need to do that. And it turns out that just figuring this out is already very, very complicated problem. And there is kind of no clear answers. Different groups, trying to estimate how much it takes to run an algorithm, the same kind of algorithm for the same application, were coming with results that were different by orders of magnitudes. So I would say the only application that I'm like pretty certain, if quantum computer magically appeared, is we will be able to run after a couple of months of kind of writing some of the necessary software for this particular hardware, is factoring. So that's a bit of kind of from the perspective of my team, so like applications team at PsiQuantum. It's a bit problematic because, well, our mission at PsiQuantum is to build the world's first useful quantum computer. And the applications team really focuses on the word useful. So we are trying to find applications which are useful and algorithms that actually give some advantage. So, like, fortunately, there is...
If I may, sorry, if I may interrupt over here, Michal. Following up on your last question on how many useful applications there might be, after answer being one, there's a lot of discussion going on Discord. Like, what do you think about other applications like optimization problems or molecular simulations? Is that something that is too far, or are you still pragmatic?
No. Okay. Let's be very clear. I think all the quantum chemistry, these are great applications. The problem is that if you try, okay, let me just get back a bit. Oh, sorry, it's like slow. If you try to go with those algorithms, those applications, if you try to take the whole chain of compilation from the high-level algorithm, such as phase estimation circuit, even earlier, of like defining the problem and doing classical preprocessing, it turns out that for some chemistry problems, the bottleneck is already on the classical preprocessing. Because if we want to calculate the data that's necessary for a quantum computer to calculate, ground state energy or whatever, well, you actually need a supercomputer to even perform this preprocessing to get input data for a quantum computer. So when you start there, then you go through those different layers of the circuits. You take one of those boxes here, and you need to write a circuit that looks something like this. And in reality, when you take certain details into account, it's like much more complicated. At each of those stages, there is a chance that like someone made a mistake. And I mean, people make a lot of mistakes in those circuits. And like, if you read those papers, they're just like full of mistakes. Sometimes non-consequentials. Sometimes they're just like, some of those subroutines are like very naive in their implementation and like unnecessarily resource hungry. But sometimes people just connected, made some connections between registers in the wrong way, and the results are just simply incorrect. And when you are trying to implement it, you only then learn that. So, going through this and then going again through all the steps of this fault-tolerant compilation to something that you can execute, this whole chain is, not necessarily something that we have today. So I'm not saying quantum computers will not be useful for solving, let's say, quantum chemistry problems. What I'm saying is, today, it's like what, July 26th, 2024. I'm actually sitting here. There's a nice backyard over, behind my window. If there you put magically a quantum computer, I would need to spend, at least probably good couple of months, if not years, of research to be able to solve one of those quantum chemistry problems, because there are just like so many open questions on how to best implement some of those routines and like how to even, do that correctly. Because when you see no. Okay, when you see a high-level diagram of the algorithm like this, the fact that someone says, well, this is a box which prepares an arbitrary quantum state, which we need for these calculations. Well, high level conceptually, that's fine. I mean, it's a correct statement. This is a box that like does that. The problem is that you need to actually implement a circuit which does that, and sometimes implementing the circuit is like very, very much non-trivial, and people just like haven't figured out yet how to do that. And fortunately, there are initiatives or like projects like Qualtran. I think Q# also has a bunch of the like explicit implementations, and I think in particular they have the double factorization kind of circuits implemented, but I'm not sure if they have implemented it to like all the details and whether you actually know exactly how to, like whether all the questions on the like around even building these applications are actually answered, and you can just take it off the shelf from like some paper and just like plug it into your applications and solve it. So that's what I meant, right? There's a lot of applications that are promising. It's just like, if it's today, we are not really ready yet.
Right. Yeah. Thanks a lot for putting some thoughts into that. This particularly clears some confusion over here. So yeah, thanks a lot.
Cool. So I will try to get to the QRE quickly, but basically what we have here is a plot with some of the costs, and it also shows another like phenomenon we see in algorithm development is you see the volume here it's not kind of how it's called, like computational volume. No, the computational volume is this, like algorithmic volume that like IonQ proposed or something like that. And the volume here is basically number of qubits times number of T-gates in the kind of first approximation. So as we can see, as the time goes, for different problems, we get better kind of resource estimates, right? So each dot here is some resource estimate of like how many resources it will take to solve particular problem. And the good thing is that all the lines are actually trending to the right. I mean, they are trending to right because right is the time, but I mean, they are trending bottom. So hopefully, as we progress, we will actually have more of the better algorithms that will allow us to run this on kind of smaller hardware, right? So that's somewhat kind of optimistic. At the same time, it's like the first improvements are usually easiest to make, and like as you make those improvements, they're only the ones that are harder. So it requires more and more effort to make that, to get the improvements. But also another point, as you can see, there are like some cryptography related, like RSA or elliptic curves. But we also have FEMOCO, we have derivative pricing, some catalysts, some Fermi-Hubbard models. So definitely, those applications are also on the map. But also I mentioned it's hard and it takes time. So for example, there is this paper that our team have published some time ago. And the problem of this was the project that I wasn't really involved, but I think it took about like 1 year. And from what I heard, the high-level structure of the algorithm was known kind of 3 weeks into the project. And the rest of this year-long project was actually figuring out the details of how you translate this high-level structure into an actually like a circuit that you can actually run, right? And really that took like 95% of the time, and the work is very meticulous and like very challenging. So usually the life cycle of working on such application projects is that you first start from trying to define the problem, and you work with domain experts to do that. And it usually takes a couple of weeks. Then it takes again a month or so to take this problem and find appropriate algorithm for that, and like make sure actually all the caveats are there are no caveats behind the algorithm, and you can actually use this algorithm for this problem and it actually makes sense. Then the biggest part, it's like algorithm instantiation and like compilation. So algorithm instantiation is just like writing down the details of the algorithm, while compilation is making sure you can translate this into something that's executable, and then lowering the resources. And it really takes good couple of months each. Then once you have the algorithm written down, you need to get the numbers that tell you, okay, how many days or how many hours it will run, and like how many qubits I need. So that's the resource estimation part. And then it's basically feedback loop. You want to get those numbers down, right? So the whole optimization. And if you sum up, the whole cycle takes easily a couple of months. If we take a look at end of the decade as a moment where we will have fault-tolerant quantum computer, then you get maybe a couple of those cycles of iterating and trying to understand the application, the algorithm, etc. Because it's safe to assume that each project like that takes a year. We have 2024. It's like 6 of iterations like that, one after another. And if I learned anything from my career as a software developer, iterating fast is really a key to get the right results. So one of the big problems is that we are not moving quickly enough. Okay, to kind of sum it up, I think the process of iterating over new algorithms and new applications is very slow, it's very painful. It requires both very deep expertise in the algorithm space, but also a lot of deep expertise in the domain space. The best projects in the applications are the ones where domain experts are working with quantum experts together, and they really are able to find this like sweet spot of what how to squeeze the best out of the most out of quantum computer in a way where we don't solve problems that are easy to solve classically, or where we can do a lot of good classical preprocessing. It's also quite error prone because, as mentioned, a lot of the work is very manual. And another problem is, well, the results are often scary. And this is, it's discouraging to be the first person in the world that estimated that even, got to this point where you are able to say something about how long it will take to run the algorithm. And then you see that the number you got is like, I don't know, like 1,000 years, right? It's like, well, we know that the trend lines are going down, but still 1,000 years is quite intimidating. So these are the problems we have, I think, with the algorithms and application development for FTQC. So one of the solutions to that is creating tools which will accelerate the analysis of those applications and drive the development of those algorithms, but also importantly, reduce the resources you need. So if we look at this plot from some other paper that we published, you see those dots are basically, right, like those resource estimates, like how many T-gates you need and like how many qubits you need. So the problem is that like creating each of those dots takes, as I mentioned, I mean, maybe not each, but like each cluster of the dots, it's usually a year-long project. And we would like to get into the world where you can just click a button and just like create a lot of them. And also then, do especially focus on those that are promising in terms of the resource counts and really drive those, because those will be the first applications, right? And the tools that allow us to do that are, the tools for quantum resource estimation. Okay, cool. So let me get to the quantum resource estimation. Okay, so it's not a formal definition, but quantum resource estimation is like process of establishing what resources are needed to run particular algorithm on a fault-tolerant quantum computer. And I would say that whenever you hear quantum resource estimation, it is actually about fault tolerance and not about kind of NISQ devices. And the reason for that is, as I mentioned before, for variational algorithms, you need to converge, and those algorithms are heuristic, and there is like, you don't know how many iterations you need to do. So it's very hard to provide a good, a good resource estimate. Well, because you just don't know how many times you will need to iterate and like when the algorithm will converge. So that's why one of the reasons why QREs for NISQ are almost non-existent. I mean, really, the paper I mentioned from Zapata, from like Jerome Gontier was, I think, definitely the best resource estimation paper for NISQ that I've seen, and really one of the very, very few. So that's just kind of FYI. So we can take a look at the QREs and classify them in a couple of different ways. And again, this is a very new, I would say, subfield. So the language might change, but the way I look at it is that often we have either logical or physical resource estimate. So logical resource estimates are, okay, here is this like abstract circuit that I can run on like any hardware, any fault-tolerant hardware. And this is where we are talking about T-gates and like number of logical qubits. And then physical is, okay, now I need to translate those T-gates to like some operation that actually run on the real hardware, and with some assumptions about the error correction codes, etc. So physical resource estimates are like much more specific, but they also allow you to actually, for example, say how long it will run, right? Because, well, it will take 10 billion T-gates, really doesn't mean much. But if you know how much each T-gate will take, then you can say something like it will take us 2 weeks to run, right? Which is a number that people can reason about. So these are like logical versus physical. Then another thing is like numeric versus symbolic. I would say that, I mean, most of the people are dealing with numeric. So, okay, here is a specific application, specific input data. And if I run it through my QRE software, I'm getting specific numbers. However, one of the projects I'm working on, Bartik, we try to write software. We wrote software that allows you to do symbolic resource estimation. So you can actually generate like expressions that are symbolic. So you can plug in an n you want, or like you can see what is actually the kind of analyze it in like a Biko notation and things like that. So that's also useful. So we have like numeric and symbolic. And then I would say it's not really classification, but it's important to know on what level of detail we are talking about those queries. Because, if you give me an algorithm, I can perhaps, maybe not I personally, but I have many colleagues that can, within 15 minutes, give you a very rough estimate of what are the resources needed to run this algorithm. But this will be very, very rough estimate. And then you can spend a year actually implementing the circuits for this algorithm and then run it through kind of very sophisticated software with a lot of kind of a very detailed model of the hardware to, well, get very detailed resource estimates. So I would say, it's whenever you're looking at these, it's important to know whether someone just did very much back of the envelope math to get the result, or they actually put a lot of effort, because as I mentioned before, the numbers might be different by orders of magnitude. Okay, so how does such QRE pipeline usually look? So like what we do to generate the QREs. Okay, this is the language that I would say, again, like you might see different language used in different places, but that's the language I like to use. So we start from a problem instance, right? The problem instance, what we mean by that is like a specific instance of the problem we are trying to solve. So saying something like, I want to find the ground state of like Fermi-Hubbard model, right? It's like, okay, but actually what's the size of this Fermi-Hubbard model, right? Like what's the kind of lattice? What are all the details that you need to specify? What's the coupling strength, etc. What are all the details that you need to specify in order to be able to say something about like specific numbers? And then another thing is algorithm, right? So, well, what algorithm I want to use to solve this particular problem? Is it quantum phase estimation with double factorization, or maybe tensor hypercontraction, or maybe something else? There's different options to choose from. Once you have these things, you need to usually a lot of kind of domain-specific preprocessing. So I mentioned tensor hypercontraction. So this is, well, a method of preparing this. Like I showed this, that in the quantum phase estimation, you have this like, U unitary. And I mentioned something about block encoding. So THC, tensor hypercontraction, is a method of like preparing that block encoding. And it turns out that it scales much better than double factorization, but it requires much more classical preprocessing. So this is like pretty important step that you need to take into account. As I mentioned before, sometimes this classic preprocessing might not work, or might just require too much classical resources. Then what usually happens, I would say, is that we go through a rough implementation of the algorithm. So you roughly know what are the high-level components. You don't necessarily know all the details, but just to get some initial numbers, you can go with that. And then as your project, progresses, you try to find, okay, which of those subroutines that I have already, identified in my algorithm, which of them are the most resource hungry, right? Okay, so for example, like QROM is a good example of a subroutine which is quite requires quite a lot of resources. So then it makes sense that if this is a bottleneck, then we will spend more time on compiling it more carefully, trying to see whether for our particular application, for our particular set of data, we can do something to reduce the resources or use, any tricks, and basically refine that. And then, you need to take the information about the quantum error correction code and some details about the hardware that you want to run your algorithm on in order to get, actually, maybe implementation is not the right word here, but to get like the physical, resource estimates. So I would say, at this stage, you can get the rough implementation, you can get some logical resource estimates that are pretty rough. Then at this stage, you can get more detailed ones where you have higher confidence. And at this stage, you can actually tie this into some like physical, like some particular hardware or QEC schemes. So what does the QRE looks like? So for example, I would say that most of the time it's just a dictionary with some data. As you can see, this comes from like some project that I did in the past. We have some number of TOEFL gates, total number of T gates at the level of block encoding, then how many times we need to repeat this block encoding, like 300,000, and then some resources for, like physicals, like given some assumptions about the hardware, it will take 1 hour to run. I don't want to kind of click the link because I'm afraid it will just break my screen sharing. But actually, if you take a look at the Azure Quantum Resource Estimator from Microsoft, they also return something that looks like this dictionary. It's just like much, much, much bigger. If anyone is interested, just like going through what kind of fields, what kind of information they return, that's already pretty useful. And speaking of Microsoft, sorry, I had like, what does a QRE look like? I forgot to fix that. So a QRE, you already seen a couple of QREs in this talk before, right? Because, well, usually this is some data that you later want to visualize. So in this case, what they did is they just visualized the QREs using different markers for different hardwares. So you can see that, for example, to solve some quantum dynamics problems, depending on some hardware assumptions, you might fall somewhere in this region, right? Which I would argue is somewhat better than what we see in this plot, because here we have just like singular points that don't give us that much information about the ranges, right? Though, to be honest, like this is, again, like comparing these two plots is a bit of comparing, apples to oranges, because here we have logical resource estimates, right? T count and logical qubits. Well, here we have physical resource estimates. So if we get back to this picture, right, you see the difference between logical and physical, right? To produce physical, we need the hardware specs. So given those hardware specs, we can get those kind of ranges of numbers. So these are like, some of the QREs. And here we have an example from one of our paper where you get what I mentioned, what I call like symbolic resource estimate, right? Or these are basically expressions analytical expressions that give you some idea of what's the scaling of particular algorithm. I mean, just LaTeX expressions, right? Like mathematical things. So maybe not particularly exciting, but nonetheless pretty useful in those, like, especially in those like first stages where we are just like trying to figure out whether it's even worth our time to, you know, to deal with this problem. Okay, I'm getting to an end with that. So why are high quality query important? Well, they allow to make informed decisions about a couple of different things. So algorithm design, you can have a query and you can see what are the bottlenecks in your algorithm, and how to improve it, right? Or maybe they give you some extra insight on why this approach is perhaps even not very good, because, for example, you can see that the scaling is just bad, and this algorithm will never be good with this kind of scaling. But also QREs are extremely important for hardware people, because imagine a situation when you work at a quantum computing company and you go to your hardware team and you say, hey, I have this amazing application that will make our quantum computer, practical and useful. And if we can solve this problem, then, the world will be a better place. And then they say, okay, so how many qubits, logical qubits, do you need to solve this? And then you say, well, I need 560 logical qubits. And they say, well, the problem is we have a device with like 550, and that's what we plan to build. So too bad you didn't tell us before, because then we could perhaps, change our plans and like tweak it to get those like 10 extra qubits. And basically, there is just like so many trade-offs that the hardware, people can make in designing their systems, that they need to have QREs at this stage to make some informed decisions about some of those trade-offs. Because we cannot just like run these. And as I mentioned, those fault-tolerant devices are pretty complicated. They take a lot of time to build. So it would be pity if we didn't have this information, how many qubits you actually need to run this, and then we build a computer which is just like a couple of percent too small to do this. Right? As mentioned before, they allow you to better understand what are the bottlenecks, what are the trade-offs, and like what's worth investing your time in, both in terms of here is the algorithm, I want to know how to improve it, but also here is like set of 5 different applications, well, which is the most promising, right? When it comes to it will be able to run in the next 10 years versus the next 50 years. And also, as I mentioned, they provide a feedback loop that allows you for rapid prototyping of the algorithms. I really like, there was a talk by Will Zhang, who then was at Goldman Sachs a couple of years ago, when he said that they used some like early QRE tools to analyze their algorithm. And they managed, using those tools, they managed to, after like, a couple of months of research, they managed to get to the exact same place with the resources that they were before. But because it turned out that they have undercounted some of the resources, they have overcounted some others, and then they identified some of the kind of issues and like just like bugs in their code. And he said that really those QRE tools were essential in just like enabling them to understand what's going on in the algorithm, to like analyze the algorithm. So, okay, what are those QRE tools? Right now, I would say there's like a couple of software packages, the ones that are I would say, most important are Azure QRV tool from Microsoft. I would say this one has the best documentation and the best tutorials, and probably a good starting point to play with that. Then there's Qualtron from Google. Also, I mean, they're all great packages, but like Qualtron from Google, it has a bunch of things implemented. It works mostly on this logical level, but like has a little bit of the hardware or like error correction stuff as well. BenchQ from Zapata, I would say mostly focused on like the whole pipeline, so like end to end. So if you are interested in actually how the intricacies of the hardware modeling influence the resources, there's like a lot of good stuff in BenchQ. For example, they have, I think it's already open source, they have pretty complete model of an ion trap that allows you to really derive some interesting resources related to the hardware. A PyLector from MIT Lincoln Labs, that's, I would say, more focuses more a bit on the application layer, allows you to build some of the circuits for the algorithms. And then there's like QRF and Barting. So these are the projects that I work on from PsiQuantum, mostly focus on the symbolic resource estimations. I think it was pretty obvious from the talk, but QRE is just like a part of the puzzle. You need to also have like algorithm definitions. You need to define those applications. You need to have all the software for the compilation. So sometimes, some people, like the 90% of getting a good resource estimations is actually focusing on like one of these things. So I would say QRE, is kind of a set of tools that like help people working on these things, but not necessarily the end goal itself. Okay, so to conclude, right, I think that the main takeaways is that like NISC and FTQC mindsets and methods and algorithms are very different. There is plenty of work that needs to be done on the development of the fault-tolerant algorithms. And also, I think I convinced you that quantum resource estimation is, this is a tool that really can help us with that. So if you would like to learn more about QRE, there's a couple of places. So we have a kind of Discord, kind of for people working on QRE, good place to ask questions. We have organized a couple of calls, so a couple of talks, so you can check them out on YouTube. I have a couple of blog posts on my blog. I'm organizing QRE workshops at IEEE Quantum Week conference in Montreal. If anyone will be there, then please come. There is also in September QRE workshop organized by, a couple of people, among others from Aalto University from Helsinki, in Helsinki actually. And then the documentation of all the software packages I mentioned is also a good place. And also, if you want to just learn more about fault tolerance, the topic is vast. There's like so many kind of angles you can try to approach it from. But my favorite resources, I would say, Game of Surface Codes from Daniel Lutinsky, already mentioned. I think the best intro point is Artur Pesach's blog. He really wrote blog posts that if he wrote them half a year earlier, they would save me a ton of time. But I had to learn the kind of hard way, a lot of the things he described. And these are amazing introductions to the topic. There are some resources on the PsiQuantum's website as well. And, reach out to people in the field and like ask them questions. I would say feel free to reach out to me. We'll be happy to, give you some resources, answer your questions, etc. And I forgot to put a thank you very much slides. So I would just say that thank you very much for listening. Thank you for your questions and thank you for having me.
And thanks a lot, Michal. And just reiterating on the point you just mentioned, that there are not enough tutorials for QRE. I think that is also a good exercise for some of the advanced participants we have. So if someone is interested in exploring the subject and preparing tutorials, I think that would be wonderful. And why don't we start a project with PsiQuantum and Womanium on exactly that? Just hinting it out there, but if something does develop, we will keep all the participants in loop. And yeah, so really looking forward to that. And thank you, Michal, once again.
Thank you very much. My pleasure. Have a good day, everyone.